Welcome back to the deep dive. You know, when most people see a standby generator, they just see this monolithic box.
Right. It's just a thing that sits there.
Exactly, a necessary evil, sort of just waiting for the grid to fail. It's the ultimate symbol of passive reliability. But if you're like us, or if you're our listener, the learner, you get that under that shell, there's this whole universe of specialized engineering.
Oh, it's an entire ecosystem in there. It's not just an engine bolted to an alternator.
Not at all.
It's way more. It's an exquisitely integrated system. You've got combustion science, you've got load management electronics, precise acoustic engineering, all working together.
And the demands on it are just immense, aren't they? It has to sit there for months, then start instantly.
And run for days, maybe in a blizzard or a heat wave. And all the while, it's got to match the power demands of a modern house without, sounding like a jet engine.
And today we're excited to spotlight a technical manual for installing and maintaining Generac air-cooled automatic standby generators ranging from 7 to 16 kilowatters.
This is the real nitty-gritty stuff.
It is. This might help you get to sleep as we discuss the technical specifications and inventory details across major subassemblies, including the enclosure, control panel, transfer switch, and various engine models like the GN410 and GT990. Let's dive in.
Our mission today is really, like you said, parts archaeology.
I love that term. We're going way beyond the glossy brochures.
We are digging into the source material, the nuts, the springs, the wire harnesses. We want to understand the specific engineering choices that let these generators cover such a huge power range.
So where do we start?
Well, funnily enough, we don't start with the cool hardware. We have to start with the legal and safety context.
The fine print.
The big print, actually. The manual is so clear on the operational constraints, and they basically define the whole design. The very first thing you see is that critical warning.
Danger of deadly exhaust fumes. All caps.
It's all caps, which immediately leads to the next rule. Mandatory outdoor installation only.
And right there, that one rule sets the physical parameters for the entire enclosure we're about to discuss. It has to be weatherproof, ventilated, and quiet.
It literally sets the perimeter, like you said. These things are designed to live completely separate from your house.
Okay, so that's constraint number one. What's the other big one?
The second one is purpose. The manual is explicit. They are not intended for use as primary power or in life support applications.
They're standby units. Emergency use only.
Exactly. And that tells the engineer everything. You're designing for transient emergency use, not for something that runs 24/7.
If they were primary power, you'd be looking at a whole different ballgame, right?
Yeah.
Liquid cooling, much heavier duty alternators.
Oh, completely different. The maintenance schedules, the redundancy, it would all have to be scaled up massively.
So with those two core rules in mind, outdoor only, standby duty, we've broken this deep dive into 4 parts. Right from the technical drawings.
Yes, moving systematically. First, the protective shell, the enclosure.
Then we'll move to the electronic command center, the control panel.
After that, the grid isolation unit, the transfer switch, super important.
And finally, the part everyone's waiting for, the actual power plants. The 3 different engine philosophies Generac uses here.
Right. The single-cylinder GN410, and then the 2 V-twin families, the GT530 and the big GT990.
We'll be calling out drawing numbers like 0F9431D.
And what's so great about these documents is that they give you a complete blueprint. You can see exactly how they standardize things while also allowing for these highly specialized tweaks for each power level.
Okay, let's unpack this. Starting with the part you actually see, the enclosure. When you walk up to one, you just see a single color, tan or gray maybe.
But the parts list tells a completely different story. It's not a simple metal box, it's a precision assembly, and it's all defined by this really smart manufacturing logistics code.
The material code legend.
That legend is an economist's dream. I love it. It shows how they standardize the actual shape of the parts, even when they're made of different materials or painted different colors.
Okay, so what are the codes?
It's simple. S is for steel, A is for aluminum,
And the colors.
N for tan, G for gray, and B for black.
So if you have a roof component, let's say part number 0F6522.
You just add the suffix. So 0F65222SN is the steel roof, painted tan. Simple as that.
And the ability to use the same tooling, the same stamps, to make both an aluminum and a steel part, that must be a huge manufacturing advantage.
It's massive, and that aluminum option, the A, that speaks directly to the outdoor-only constraint we mentioned.
Ah, for coastal areas. Salt in the air.
Exactly, or any high-humidity place where rust is a problem. You pay a bit more for the aluminum, but it's basically an insurance policy against corrosion. It keeps the unit looking good and, more importantly, keeps the enclosure intact for decades.
And I see a note here that even the fasteners change a little with the aluminum. They standardize on locking flange nuts.
That's a really sharp detail. Aluminum is softer than steel, right?
Right.
So if you just torque a standard nut onto it, you could pull the screw right through the panel or crack it. But a flange nut spreads that load over a wider area.
So it prevents damage. And the locking part is for the vibration.
Precisely. Even with a smooth V-twin, there's always vibration. The locking feature makes sure those panels don't work themselves loose over time. It's a subtle choice that just reinforces the quality of that premium option.
Let's move down to the foundation. The whole thing sits on this specific pad.
Item 1, the Pay-T, 24x48 with mounting holes. It's not just a slab of concrete, it's designed to ensure proper air circulation underneath and give a perfectly stable, level surface.
And the anchor points are metric. S screw HHC M8-1.25x25.
The fact that they use metric hardware right down to the anchor bolts, that says a lot about their global manufacturing strategy.
Standardized parts, easier supply chain.
Absolutely. Metric fasteners are the world standard. It means they can get predictable torque values and strength no matter where the unit is assembled or installed. It speaks to a really impressive global consistency.
Okay, let's go inside the box. Airflow. This is where it starts to get interesting because the parts change based on the power output.
This is a critical point of divergence. You see two different scroll FM part numbers.
Right, 0F8871 for the 7 and 10 kilowatt models.
Yeah.
But then it jumps to 0F8080 for the bigger ones.
And you have to ask why. It's because heat dissipation doesn't scale in a straight line with horsepower. The GT990 in those bigger units is a much larger engine, it's running at a higher power density, and it's just generating way more heat.
So the bigger scroll isn't just for a bigger fan, it's to manage the sheer volume of air you need to push across those hot cylinder heads.
And across the specialized oil cooler on the GT990, which we'll get to, it's a modification driven purely by thermal physics.
And that specialization continues with the internal divider panels.
Yes. 3 different parts for the panel, alternator divider, one for each engine family.
So that panel separates the hot, noisy engine part from the sensitive electrical alternator part.
Correct. And the fact that there are 3 different part numbers tells you that the physical footprint of the engine, the location of the exhaust, the whole cooling air path, it all changes fundamentally between the single cylinder, the medium V-twin, and the big V-twin.
They're not just using a one-size-fits-all panel with a few extra holes punched in it.
No, they're maximizing the thermal efficiency for each class. The bigger the engine, the more tailored that, and really bother the neighbors. The fact that they're wrapping the muffler box in foam shows they're trying to contain those specific frequencies right at the source before they can vibrate the whole enclosure. That foam is likely a very specific, high-density, closed-cell material engineered just for that noise profile.
It's the difference between a loud machine and a product people actually want in their backyard.
Absolutely. And to keep that acoustic and thermal environment stable, the whole thing needs to be sealed perfectly.
Which brings us to item 36. 11 quantity of gasket, extruded trim.
11 separate pieces of gasket.
That sounds like a lot of work during assembly, but I guess it's not negotiable.
It is mission critical. Think about the cost of a failed gasket that lets moisture into the control panel 5 years down the road. It's catastrophic. The cost vastly outweighs paying a worker to install 11 pieces of weather stripping on the assembly line.
So that rubber gasket keeps its seal even when the metal expands and contracts with temperature swings.
Exactly. It stays elastic and watertight. It's a long-term investment in reliability.
Okay, let's wrap up the enclosure with connectivity. The external connection box.
That's the demarcation point. It's where the electrician hooks everything up, but the wiring inside the box changes significantly.
Right, we see different harness, engine parts, and 3 different harness generator to external connection box parts. Why 3 for that connection box harness?
It's all about the complexity of the engine it's serving. The 7 kilowatt system has a simpler mechanical governor. It doesn't have all the sensors the V-twins do.
So it needs a simpler wiring loom.
Exactly. The 0F5440 harness, the 10 kilowatt 0F9328 is the mid-range for its more advanced V-twin, and then the 13 and 16 kilowatt 05478 need the high-end harness to handle all the sensors and controls for that big GT990. The electrical integration is custom engineered for the power plant.
Okay, so from the shell to the brain, here's where raw mechanical force becomes smart, managed electricity. We are inside the control panel.
The command center. This is where the decisions get made. When to start, when to protect itself, how to keep the engine speed stable under load.
And the clearest, the absolute clearest demonstration of scaling in the system has to be item 1, the main circuit breaker.
Oh, absolutely. The size of this component is dictated purely by the physics of power output. It's fundamental overload protection.
So for the 7 kilowatt unit, which puts out about 30 amps, you get a 30 amp breaker.
A 30A by 2P 240V breaker, to be precise. That 2P is important. It's a double pole, so it protects both of the main 120V legs feeding the house simultaneously.
And then it just climbs from there in perfect steps.
Perfect steps. The 10 kilowatt A jumps to a 45A, the 13 kilowatt A gets a 55A, and the top-end 16 kilowatt needs that heavy-duty 65A breaker.
And they're swapping out the whole component, not just like tweaking a setting inside.
Exactly, which tells you the alternator windings themselves are designed for distinct, non-overlapping maximum current. It's real hardware scaling.
And at the very core of this panel is the brain itself, the controller assembly. We see a specific part number, 0F1504, for the 7 kilowatt model.
Right, and that controller's programming has to be fundamentally different from the ones for the V-twins. It's the keeper of the operational logic.
Because the V-twins use a sophisticated electronic throttle.
Right. The controller for a V-twin is managing ignition timing, fuel flow, RPM adjustments, all based on real-time electrical load. The 7 kilowatter, though, that one relies on an old-school mechanical governor.
So the 7 kilowatt controller is talking to springs and levers, while the V-twin controller is talking to sensors and motors.
Precisely. The complexity of the brain scales with the complexity of the engine it's running, and this is highlighted by what's missing from the 7 kilowatt panel.
Yeah, I saw this. Item 4, the RLA 12V25A SPST, is explicitly marked, Nenon 7kW.
And even more importantly, item 16, the current transformer, idle control, is also Nenon 7kW.
Okay, so the current transformer, let's break that down.
The CT is the critical sensor for modern engine control. It's a little donut that wraps around one of the main output wires, and it non-invasively measures the current, the electrical load.
So it's feeding real-time load data directly to the controller.
On the V-twin models, yes. This means the engine knows exactly how much power is being drawn. It can adjust the electronic throttle before the RPM even has a chance to dip.
Which gives you cleaner power and better fuel efficiency because it's only using as much gas as it absolutely needs.
That's the whole point. The 7 kilowatt doesn't have that. Its controller has to wait for the engine speed to physically drop under load before the mechanical governor kicks in and opens the throttle. It works, but it's a slower, less nuanced reaction.
A cost-saving measure for the entry-level model. It's robust, but less efficient.
Exactly. And the missing 12V relay is probably tied to that. It likely handles a high current accessory for the V-twins' electronic fuel or choke system, something the simpler 7 kilowatt just doesn't need.
We also see the 4-position terminal strip in there.
That's just the organizational heart of the control wiring. It keeps all the low voltage signals from the transfer switch neat and tidy.
Okay, now this is interesting. The specialized hardware. Item 18, the M3 0.5 TRI-CUT, is also marked Nenon 7kW. What is a trick nut?
So a trick nut is a type of self-locking nut. It has 3 lobes that slightly deform the threads of the screw as you tighten it, which creates this incredible resistance to vibrating loose.
So why do the V-twins need special vibration-proof hardware when you'd think the single-cylinder engine would vibrate more?
Ah, that's where the nuance is. The single-cylinder engine, the GN410, has a massive internal balancer to cancel out most of that primary vibration at the source.
Okay.
The V-twin, while it's inherently smoother, produces a different kind of vibration, a different frequency, a different amplitude, especially at high RPM. And those specific high-frequency harmonics could, over time, loosen standard fasteners on a sensitive circuit board.
So the trick nuts are there to protect the sensitive electronics from their V-twin neighbors.
That's a perfect way to put it.
Let's talk about the power supply for the board itself. Item 30, the XFMR 24016 V1 VAN56 WPTC.
That's the transformer. It steps the raw 240V generator output way down to the low voltage DC the controller and battery charger need, and that WPTC at the end is the key safety feature.
Okay, explain PTC for the learner.
Think of it like a smart, self-healing fuse. PTC stands for positive temperature coefficient. When too much current flows through it, say from a short circuit, the material inside heats up and its electrical resistance skyrockets, blocking the current.
And then what happens?
Once the fault is cleared and it cools down, the resistance drops and the circuit just works again automatically.
You don't have to send a technician out to replace a tiny fuse every time there's a momentary spike.
Exactly. It builds resilience right into the power supply, which is critical in a harsh environment like a generator.
And finally, you have the human interface. The big switch, rocker DPDT on-off on.
Even with all this digital complexity, the most important commands, auto, manual, off-on, are handled by a big, chunky, reliable switch. DPDT just means double pull, double throw. It's built to handle multiple circuits cleanly. It's the low-tech guarantee that you can always tell the digital brain what to do.
All right, so from the brain to the muscle, let's talk about the transfer switch.
If the control panel is the intelligence, the transfer switch is the traffic controller. And it's also the legal gatekeeper for your house's electricity.
Its number one job is grid isolation, right?
Its number one non-negotiable function. It has to physically guarantee that your house is disconnected from the utility grid before the generator connects. That prevents dangerous backfeeding that could kill a utility worker down the line.
And once that isolation is confirmed, its second job is managing the load.
Right, deciding what gets power. And the first variable we see here is just physical size. The docs show 4 distinct load center sizes.
8, 10, 12, and 16 circuit models. And each one has its own unique cover.
That modularity is so important for the installer. They can perfectly match the transfer switch to what the home actually needs. A small house might just need the 8-circuit model for the fridge, furnace, and a few lights. Saves the homeowner money and complexity.
But no matter how many circuits you have, the actual switching is done by one core component, item 3, the transfer switch home standby 100A 2P250V.
That is the main contactor. That's the muscle. It's rated for 100 amps of continuous service. And inside, the heavy copper contacts are thrown by 2 specialized coils.
The coil utility and the coil standby.
They're powerful solenoids. The control panel sends a signal, and the coil creates a magnetic field that physically slams the contacts from one position to the other. It's a near instantaneous clean break before make transition.
And using separate coils for utility and standby, that's for reliability.
It's for redundancy and a clean switch. When utility power comes back, the utility coil energizes and pulls the contacts back. It prevents any chattering or arsing that would just destroy the contacts over time. It's built for thousands of cycles.
Okay, let's get into the circuit breaker matrix, items 32 to 37. This is where you can really see the philosophy change. The circuit count goes up.
This matrix is the clearest guide to how Generac expects people to use these. Look at the 8-circuit model. It's almost all 15-amp single-pole breakers.
So lighting circuits, standard wall outlets, the bare essentials.
The survival essentials, exactly. It's got one 20-amp double-pole breaker, probably for a well pump or maybe a dedicated fridge circuit. That's it.
Now compare that to the 16-circuit model.
It's a whole different world. You still have the basic 15-amp breakers, but now you've got 5 20-amp single-pole breakers for things like kitchen or garage circuits, and more importantly,
you get the big ones, the 40A2P and the 50A2P.
And those are the key indicators. That's the shift from essential backup to comfort backup. Those breakers are for the huge 240V loads.
An electric clothes dryer, central air conditioning.
A big pool pump. This proves the transfer switch isn't just an on-off switch. It's a fully customizable, heavy-duty distribution center that lets you segregate your critical home infrastructure.
And to handle all that amperage, you need serious connection points. Item 23, 6 quantity of LUG SLDLSS 10, hashtag 14X916 ALCU.
Let's decode that. SLDLSS means solderless. It's a mechanical clamp. In high amperage situations, solder can actually melt or degrade over time with heat cycles. A mechanical lug is way more reliable.
And the 10 to number 14 rating, that's a huge range.
That's massive versatility. It means that one lug can accept a giant 10-gauge main feeder wire or a standard 14-gauge wire. And the ALCU means it's rated for both aluminum and copper wire.
Which gives the electrician flexibility depending on local code and material costs.
Right. And you get 6 of them because you need connections for utility input, generator input, and house load output. 2 hots and a neutral for each.
And just to bring it all home, we see that specialization again. 4 unique wiring harnesses for the load center.
A classic case of customization through wiring. The physical layout of an 8-circuit panel is totally different from a 16-circuit panel, so the little low-voltage control harness that connects the switch to the control board has to be tailored precisely for each one.
It just eliminates any chance of human error during installation.
It guarantees the system works as designed, even if the difference between the 2 harnesses is just a few inches of wire.
All right, we've built the house, we've wired it up. Now let's fire up the engine. We're diving into the most powerful one in this line, the GT990 V-Twin.
This is the power plant for the 13 and 16 kilowatt units. And this thing is built for serious, high-output, air-cooled performance.
Looking at the crankcase drawing, the internal parts just scream high performance. We've got two piston flat-top DI-90 coated.
Let's talk about that coating. It's usually a Teflon or a polymer matrix, and it serves two critical purposes in an engine like this.
Okay.
First is friction reduction, especially during a cold start when oil coverage isn't perfect yet. Second is thermal tolerance. A big V-twin generates a ton of heat, and that coating helps the piston maintain its exact size and shape under high temperatures
So it keeps the tolerances tight and the combustion efficient.
for the entire life of the engine. And it's paired with that heavy-duty direct drive crankshaft, which means no belts, no transmission losses, just pure mechanical power straight to the alternator.
The lubrication system on this thing looks pretty complex.
It is. It has to be. The detail I love is the pressure relief system. It uses two spring oil relief and two ball 12D oil relief components.
Why two of each? Why not just one big one?
Because oil viscosity changes so much with temperature. On a cold start, the oil is thick like molasses, and the pump pressure can spike dangerously high. This system acts as a bypass valve. By having two, maybe staged at different pressures, it can smoothly regulate oil pressure across the whole operating range, from freezing cold to scorching hot.
And the seals have to be top-notch. I see two different crankshaft seals, and they're both designated green.
The different diameters are just because the shaft is a different size at the front and back, but that green color code is important. It often means it's made of a specific high-performance material like Viton, which is way more resistant to heat and chemicals than standard black nitrile rubber.
So it's another one of those small details that ensures long-term reliability.
A leaking crank seal would be catastrophic in an air-cooled engine. This is essential.
Moving to air and fuel, we have the assembly, Mixer Airbox 990.
And it uses specialized gas fittings. You see that barbed elbow. VS likely stands for vapor service. It's specifically rated for pressurized natural gas or propane vapor.
But the most intricate part here looks like the choke. It's mechanical, but it's driven by a solenoid, 6 VDC.
This is a beautiful piece of electromechanical design. Getting the air-fuel ratio perfect on a cold start for a big V-twin running on gas vapor is absolutely crucial,
So the control board sends a little 6-volt signal to the solenoid.
which physically moves the choke arm just the right amount. And then all those little springs make sure it snaps back open reliably once the engine fires up and the solenoid turns off. It's electronic precision meeting mechanical reliability.
And cooling this beast must take a huge amount of effort. Item 101, the FAN, NYL says 101 quantity.
That's referring to the number of molded fins on the flywheel. Think about it. This engine is making 16 kilowatts of power, which means it's also making a ton of waste heat, all trapped inside that acoustic enclosure,
So that 101 fin fan is basically a giant centrifugal pump.
moving massive volumes of air over the cylinder heads in the oil cooler. And the geometry of those 101 fins is carefully designed to create maximum airflow with minimum noise. It's a delicate balance.
And holding that whole rotating mass on is a huge M24 nut.
M24 is a very large nut. That just confirms the enormous torque needed to keep that flywheel from flying off the crankshaft. Between the starting, stopping, and dynamic loads, the forces on that connection point are immense. That hardware ensures it never, ever loosens.
Okay, so that's the top of the line. Let's step back down the power curve and look at the smaller engines.
Right, let's analyze the 10 kilowatt and 7 kilowatt units. The 10 kilowatt is powered by the GT530, which is still a V-twin, but it's a smaller mid-range package.
And the first big difference I see from the GT990 is the oil pump. This one uses something called a gerotor system.
A gerotor pump is a type of positive displacement pump. They're known for being really efficient, really reliable, and very compact. It delivers consistent oil flow without the complexity of that dual ball relief system we saw on the big engine.
So it's a simpler but still very effective design for the lower horsepower.
It's a smart choice, a perfect balance of performance and simplicity for that size class.
And protecting this system is an oil pressure switch, Hobby's 5 PSI.
That's the engine's last line of defense. If the oil pressure drops below 5 psi for any reason, a clog, a pump failure, low oil, that little switch tells the control panel to shut the whole thing down immediately. It's the critical link between a mechanical failure and electronic protection.
And looking at the flywheel for this engine, I see another interesting fastener detail.
The M20 nut, yes, but the real key is the washer that goes with it. Item 108, the washer Belleville. That's a Belleville washer.
So it's not flat, it's cone-shaped, it's a spring.
It's a spring, and it's vital for the flywheel because of thermal expansion. As the engine heats up and cools down, the metals expand and contract. A normal flat washer could let the nut lose tension, but the Belleville washer acts like a giant continuous spring, maintaining a constant clamping force on that nut no matter what the temperature is.
So they're one of those tiny parts preventing catastrophic failure.
It's brilliant, simple engineering.
Okay, now for the biggest philosophical departure. The GN 410, the 7 kilowatt single-cylinder engine, the number one challenge here has to be vibration.
Oh, absolutely. A single-cylinder engine naturally creates this massive thumping vibration as that one big piston flies up and down. And the solution is item 26, the balancer.
It's a counter-rotating mass inside the engine.
It's a mechanical necessity. Without that balancer, the generator would literally shake itself in its concrete pad to pieces. It adds cost and complexity, but it's the non-negotiable part that makes a single-cylinder engine viable for this kind of application.
And the second huge difference is the governor. We talked about the V-twin's electronic controls. This is pure mechanics.
It's classic reliable engineering. It works entirely on centrifugal force. There's a governor gear inside the crankcase with little flyweights on it.
So as the engine spins faster, the weights fly outward.
Right, and they push on a spool, which pushes on an arm, which is connected by a rod to the engine's throttle plate. It's a whole chain of physical connections.
And the speed is set by the tension in all these springs. Spring governor, spring secondary, spring idle returning.
Exactly. The main spring is calibrated to resist the force of the flyweights at the target RPM. When a load hits the generator, the RPM starts to drop, the flyweights pull in a tiny bit, and the spring tension takes over and pulls the throttle open to compensate.
A purely mechanical feedback loop.
Extremely reliable, but it needs precise physical calibration, a sharp contrast to the digital precision of the V-twin's controller.
And one last detail on the GN 410. In its exhaust system, there's a unique part called a bellows.
This is so important for the single cylinder. All that harsh vibration we talked about, it gets transmitted right into the rigid steel exhaust pipe. The bellows is a flexible accordion-like metal joint.
So it acts like a shock absorber for the exhaust.
It absorbs the thermal expansion, but crucially, it isolates those relentless vibration pulses from the single cylinder. It prevents the exhaust pipes from cracking from metal fatigue. It's a small, cheap part that saves the whole structure from shaking itself apart.
Okay, for our last section, let's tie it all together by looking at the fuel regulator systems.
This is maybe the best example of Generac's modular engineering strategy.
Yeah.
These regulators take the high-pressure fuel from your house and knock it down to the low, stable pressure the engine needs.
And when you look at the parts diagrams, the level of standardization is just incredible.
It's stunning. Across the entire range, 7, 10, 13, and 16 kilowatt, they all use the identical core components, the same housing, the same solenoid coil, the same crucial diaphragm, the same internal lever.
That makes so much sense from a logistics and cost perspective.
It's brilliant. The most complex, high-precision part, that diaphragm assembly, is the same for every single model. It minimizes their spare parts inventory and maximizes their production volume on that one critical component.
The differences only show up in the tuning and how it interfaces with the engine.
Exactly. If you look at the regulator for the smaller engines, you see an adjuster screw and a pin, limited adjustment, but only on the 7 kilowatt model.
Why would the smallest model be the most adjustable? That seems backwards.
Because it's the one with the mechanical governor. That system relies on a very precise, very stable relationship between throttle position and fuel flow. Since it doesn't have the V-twin's smart electronic controls, it might need a little physical fine-tuning of the fuel pressure during installation to get it running perfectly.
And the limiting pin is to make sure the technician can't adjust it way out of spec.
It ensures they can tune it, but they can't create an unsafe condition.
Okay, now for the big GT990. Its adaptation is all about fuel volume, isn't it?
It is. The regulator doesn't feed directly into the mixer on the big V-twin. It feeds into this critical component called the ASSY fuel system plenum.
So the plenum is like a little fuel reservoir, a buffer.
That's a perfect analogy. Think about the demand. When a 16 kilowatt generator suddenly gets hit with a huge load, like a 5-ton air conditioner kicking on, it needs a massive instantaneous gulp of fuel to avoid sagging.
And the regulator alone can't react that fast.
It can't. There would be a split second of fuel starvation, maybe causing a brownout or a stall. The plenum holds a ready volume of low-pressure gas right there at the engine, so that instantaneous demand is met immediately. It gives the standardized regulator a fraction of a second to catch up and refill the buffer.
It's the high-performance interface that lets a standard, low-cost part support a high-demand engine.
That beautifully ties the whole system together. standardize the core components, and then engineer specialized interfaces like the plenum or that Belleville washer to solve the unique problems of the higher-powered models.
This has been an incredibly extensive deep dive. We've gone way beyond just the metal box. We've gone from material codes, S for steel, A for aluminum, all the way to the internal philosophies.
We saw the control board protected by a self-healing PTC transformer and secured with special trick nuts.
And we learned that the real difference between a 7 kilowatt and a 10 kilowatt unit comes down to that little current transformer, the sensor that enables truly efficient engine control.
We dissected 3 totally distinct power plants. The 7-kilowatter, relying on a physical balancer and a mechanical governor, and the V-twins, using high-performance seals and specialized pumps to handle their power density.
The big takeaway is that this single product range is not one product at all.
It's a highly scalable, modular family of systems, each one specifically engineered for its individual power target.
And for you, the learner, understanding why a part is included or why it's specifically excluded, that's your shortcut to being genuinely well-informed. It lets you see the engineering trade-offs behind the spec sheet.
Understanding the system relies on respecting the details.
Which brings us to our final, provocative thought, drawn right from this manual. We've seen that this whole range depends on thousands of precise components, from that huge M24 flywheel nut down to tiny little screws. Considering everything we've looked at, what single component, if lost or damaged, represents the single greatest point of failure across all these models? The one that requires a massive shutdown to replace the most inexpensive part.
Well, the answer lies deep inside the heart of that big GT990 lubrication system. Item 22 on that engine drawing is the O-ring .49 IDX.07 THCK.
A tiny O-ring.
It's minuscule, barely half an inch across, but it's located somewhere deep inside the oil pump assembly or a critical pressure passage in the engine block. If that O-ring is forgotten, or gets nicked during assembly, or just fails, the engine immediately loses all critical oil pressure.
And the result is catastrophic.
Instantaneous, catastrophic engine seizure. A several $1,000 failure, all caused by a part that probably costs pennies. It just demonstrates that in any complex machine, the integrity of the whole system is entirely dependent on the flawless function of its smallest, cheapest, and most easily overlooked component.
The ultimate lesson in mission-critical nuance. Thank you for joining us for this deep dive into Generac's mechanical masterpiece.
We'll catch you next time.